All right, so now we've got our panel on geological storage of hydrogen. So Mark Shuster, our director of our Bureau of Economic Geology, will moderate with Andrey Bakulin from Bureau of Economic Geology, Harold Evin from Vallourec Group, and Capucine Saikia-Courault from Geostock Sandia.
Hi, good morning, everybody. So let me, as the panelists take their seat, just introduce myself and this session. So as Brian said, I'm Mark Shuster. I'm interim director at the Bureau of Economic Geology, and I'm also the principal investigator for our GeoH2 and Industrial Affiliates program here at UT. And I'll say a little bit more about that. The setup for this session is I want to set the scene and basically pose a few questions. First, the big question is, why does geological storage of hydrogen matter? I then want to pose the questions, what are the biggest challenges, not only in storage of hydrogen, but also in transportation of hydrogen? What sort of research is needed? And I think an important one, particularly for this forum, is how could industry and academia collaborate in such a way to facilitate solutions? So those are the questions we're going to go through. I'm going to start off with a short presentation to set the scene. Then I'll introduce my fellow panelists. And then we'll have presentations from each of them, and then come back to these questions, and then open it up for any questions you might have from the audience. So with that, let me go ahead and start off. So we've heard a lot this morning already about low carbon intensity hydrogen and how it potentially could fit into a low carbon economy. And the reasons that we're even talking about hydrogen is that it has a potential for reduced or low carbon emissions, either from electrolysis using renewables or nuclear, or from methane reforming using fossil fuels or coal gasification, as long as there's carbon capture and storage associated with that. So you have multiple ways that you can generate hydrogen. You have multiple uses as well. So many different uses, either as a feedstock for manufacturing purposes, various industries, or as a fuel, and we heard about that earlier as well. The great thing about hydrogen is it's molecular energy. It's transportable. And also this opens the advantage of storing this energy indefinitely. And particularly with geological storage, you can increase that volume of hydrogen that's stored, the capacity, so that it can help with this whole challenge, really, of how do we scale this up for a global economy. So with that in mind, just by way of background, so I've been at UT here for 8 years. Before that, I was with Shell for 30 plus years, retired from Shell. And so I'm showing a diagram actually lifted from my alma mater. It's a few years old, but I think it gives us a range of what we might expect with regards to projected global demand of low carbon intensity hydrogen by 2050 for the net zero scenarios. So low is shown there. I don't know, you can see the pointer, not very well. But you can see that in the blue bar. So, roughly 200 or so up to a maximum, and I think this is from the fuel cell estimate, close to 700. IEA has recently, relatively recently, this 2023 numbers, come up with an estimate of about, for their net zero scenario, about 430 million metric tons of hydrogen per year for 2050. So, it gives you a kind of range. I mean, we don't have crystal balls, We don't really know, but it gives you a feeling of what is going to be required in terms of demand for hydrogen. And we're talking about a scale here where the infrastructure is fundamentally important. These aren't little pilot projects. These aren't small little hubs. This is basically looking at schemes where a global connectivity, certainly countrywide connectivity, transportation, delivery, storage are all going to be important. So if we take now, just going with the IEA estimates and what that means in terms of both pipelines as well as underground hydrogen storage requirements by 2050 for their net zero scenario, we're looking at, for pipelines, a 40-time growth of what's available right now for hydrogen pipelines. But if you look at storage, that's a 1,200-time growth. And this equates to, and we're going to discuss this in some detail in our panel session today, is a significant number of salt caverns. We need 12,000 salt caverns for indicative storage of basically 300 tons of hydrogen per cavern. And you might be able to double that, depending on the cavern. Some caverns may be smaller, but it gives you a flavor. And if we were to open up depleted fields or even saline aquifer for hydrogen storage, we still need a few thousand of these depleted fields. And so it is a significant challenge for us, particularly us that are working in this subsurface energy space and the infrastructure space, to figure out how we can get on top of this in order to make this reality happen. This is a challenge. It's a really huge challenge. So what we're doing here at UT is we recognize this challenge, and this is why we actually initiated the work. Because what we are really keen on is, what is it going to take to basically realize a reduced carbon future at a scale that actually matters? And to do that, we have to focus on geological storage. We really have to focus on how the storage and transportation and delivery fit into the broader infrastructure, and what are the techno-economics, and where, how does this fit within the value chain? And also, some of the work we're doing, and we're not going to discuss today, but is looking at what are some novel concepts that potentially can be developed to generate hydrogen from the subsurface, geoengineer hydrogen generation from subsurface, either using fossil fuels or what are called ultramafic rocks to generate hydrogen. And also look where we could potentially find naturally occurring hydrogen to help with potentially the supply. Those are novel, nascent concepts, but all deserving some interest. And so we've started this consortium. Our main focus is really on the storage aspects and the techno-economics as they relate to the value chain. And we are privileged to have support from the companies that are shown on that slide, who also recognize that we're in this for the long game. It's going to take a lot of time. It's going to take a lot of research to be able to get at solutions that are meaningful. And I want to acknowledge, and I show this slide in particular because we have several of the team members that are here today. And or spanning the disciplines from reservoir engineering to geology, geophysics, economics, petrophysics, and this is what it takes. These are very complex problems, and so you need this range of disciplines to be able to address these questions around geological storage in particular. So hopefully you'll have an opportunity to meet with some of these people during lunch or later in the day. But I want to acknowledge and thank them for their contributions. So with that, we're going to segue now into discussions, presentations, and then discussions with the panelists. And I'm going to go ahead and introduce all the panelists, and then we'll come up, or each of them will come up and present. So the first introduction is for Capucine Saikia-Courault. And Capucine is a principal geologist at Geostock Sandia, a company which provides consulting, engineering, construction management, operations, and maintenance for all underground storage techniques. Over the past several years, Capucine has been managing projects for the specificity of hydrogen underground storage. Capucine graduated as a geological engineer from École Nationale Supérieure de Géologie in France. Hopefully I didn't slaughter that. And did an exchange program with Universitat Politècnica de Catalunya. Capucine has 17 years of experience in the underground gas storage industry. The next panelist is Harold Evin. I think I got that right, Harold. Thanks. With a PhD in material engineering and corrosion. He has started his career at ArcelorMittal Stainless Group, leading activities in material development. Then he joined Vallourec Group, which is a world leader in seamless pipe manufacturing for the energy sector, where he has held several positions in R&D and operations. Today, Dr. Evin is CCUS and Hydrogen Business Director for Vallourec. He oversees Vallourec global strategy, providing the industry solutions and services for safe hydrogen transport and storage infrastructure. And Dr. Evin has also 17 years of experience in the steel industry. The third panelist is Dr. Andrey Bakulin. He's a research professor at the Bureau of Economic Geology, and in his current role, he also leads another consortium alongside Professor Sergei Formel with a focus on land seismic and advanced monitoring technologies, while developing new instrumentation and techniques crucial for supporting energy transition. He also leads the hydrogen injection field test at the Devine test site that the Bureau of Economic Geology has near San Antonio, Texas. And this test is focused on hydrogen storage and innovative monitoring technologies. Andrey has over 25 years of industry experience. He's worked in reservoir characterization, monitoring has been pivotal, and at Shell, he led virtual source monitoring initiatives using downhole sensors and spearheaded tube wave and real-time completion monitoring projects, emphasizing cost-effective in-well solutions with fiber optic sensors. At Saudi Aramco, he directed the seismic monitoring program, including field feasibility studies and successful field monitoring of a CO2 EOR pilot in a carbonate reservoir. He's played a key role in designing and demonstrating the first industrial hybrid monitoring systems with 1,000 buried sensors and oversaw the processing and interpretation. And Andrey has also invented and field tested the smart distributed acoustic sensing uphole acquisition system featuring vertical arrays on a single fire, which is an innovative design. So with that, warmly welcome all the panelists. And now I'd like to ask Capucine to come up to give her presentation. Capucine.
Good morning, and thanks a lot for the opportunity to participate to this hydrogen conference. And today I will speak about the underground storage aspect of hydrogen, and just like the different technology, like possibility to store like hydrogen underground, and really like the pros and cons at very high level, but to get a good like high level summary. So what you can see is that you can store like hydrogen in a gaseous form, like in a soil cavern. You can also do it like in a depleted field or like aquifer, what we call like porous media. And it would really not make sense because of a very low pressure to be like in a hard rock mine cavern. That's why we did not place it as an option. And it is also a possibility to store it in a lined like hard rock mine cavern. So these are like the three possibility to store hydrogen underground. One thing to keep in mind is the project to store underground are major project. So it's really it becomes economical when you are looking at very large quantity of hydrogen, and that's really when you can use a hydrogen underground storage. And the advantage, and it really relates to the way as of today it's used in the natural gas market. It's a low maintenance. It's a very limited footprint if you would compare to storing the same quantity at surface, and it's a very secure way to store high pressure gas. And so just to present a little bit the different solution. So salt cavern, it is done as of today at an industrial level within 3 caverns in Texas and 3 caverns in the UK. And it has been done in the UK, the hydrogen storage was developed in the 70s. And in Texas, the cavern, one was developed in the 80s, one in 2007 and one in 2014. So this it is already done at industrial level. Maybe just to give you a perspective on how it is currently stored and how we want to use storage of hydrogen with energy transition, is that right now it's used a small quantity of hydrogen is imported into the cavern and exported from the cavern on a daily basis. Within the energy transition, we are looking at using hydrogen storage for peak shaving. So over a couple of days, let's say when we have a winter storm, we will need to empty most of what we call the working gas of the cavern. So we are looking at emptying almost half of a cavern. So from a thermodynamic perspective, things have to be checked, because it's not the way it is currently operated. And so the advantage of salt cavern is that it's you can really have a high flow rate. It's a very low cost, and you can look at converting existing salt storage salt cavern, which are currently used for natural gas, but it's really a case by case solution. And the drawback is that salt is not everywhere. Here in the Gulf Coast, we have we are lucky that there's a lot of salt domes, but it's not the case in many parts of the world. And you need a lot of water to leach the cavern, and you will produce a lot of brine, so you'll have to find a way to dispose it or to repurpose it. And also you will need roughly 50% of your cavern will be cushion gas, which will not be usable during the lifetime of your cavern. And there are some ways to recover it towards the end. And the next option is to look at a porous media, so a depleted field or a saline aquifer, if we can prove that there is a trap within this aquifer, so the hydrogen will stay where we store it. The advantage is that you can really use it for extremely large volume, and also that it has it's a very good option for looking at extremely large storage capacity, and it's the cost is efficient once again for very large facility. And the drawback is that you do not have depleted field or aquifer with a trap everywhere. So this is really geology driven, and you do need the same a cushion gas, which is a high percentage of your storage, and this one is not recoverable. And also the particularity of depleted field, and a lot of ongoing research is being done right now, and as we mentioned before, both with industry and academics, it's the potential reactivity of the hydrogen with the existing water in the reservoir. So this really is a case by case. We cannot say it will work. It has to be tested for each site to ensure that it can work. And the other one is a little bit more unique, and this one is more in a very early development phase. This concept has been tested back in the early 2000s for other type of storage, other type of product in South Korea, and we were involved in this pilot. It's because in the hard work you cannot. You would mine really a traditional mining, and you would line your cavern, and So that would allow you to like store the hydrogen at a higher pressure, so make it like a quantity which is economic to like store. And so it is like the most costly solution like in general. However, like if you do not have salt, or if you do not have like adequate porous media, and also if you are looking at maybe like at some major like import-export like terminals and things like this, it can be like an option for like for your project. So really these three solutions have pros and cons, and if a project for like requires hydrogen underground storage because it's at a large scale, the three of them have to be looked at, and it's really site specific which one will make like the most sense like for storage. And just like a last slide that shows like just some like levelized cost of storage for hydrogen. So you can see that the salt cavern is generally like on the least expensive side. But once again, you do not have salt everywhere in the world. And then the depleted like field are like depleted field and aquifer are like maybe like the second tier. And then the rock cavern, it really depends like on many parameters, but it's the ones that potentially like would be like the most expensive like for underground storage. And I think that's really like about it for this high-level summary. Thank you.
Good morning, everyone. I would like to start by thanking the University of Texas, as well as the French consul and her team, Assi Emmanuel, in the assistance, for giving me the opportunity to speak a little bit about what Vallourec is doing in the space of hydrogen storage. So first, a quick introduction about Vallourec. Who are we? So we are a French company with more than 130 years in the industry of energy, providing seamless pipe and connection. Here in the US, so we have an R&D plant, which is in Houston, as well as some manufacturing. We have, I will say, producing more than 1 million of steel seamless pipe per year, and providing our solutions for the energy production. Here in the US, so our manufacturing is based in Youngstown, Ohio, where we have an integrated steel mill. So we are producing the steel, rolling it, providing the seamless pipe and the threads for OCTG and tubing casing type of products. We have a heat treatment plant in Oklahoma, Muskogee, and as I was mentioning, beside our R&D, we have also our regional headquarters in Houston and finishing lines. So globally in the US, we are around 4,000 people working, delivering premium products for the energy sector. When we speak about salt cavern and salt cavern development, so Capucine mentioned that it is indeed an economical way to store hydrogen. Today you have here a map of where the salt dome are indeed existing, salt cavern opportunity can be developed. Europe is quite active on the topic. US and Canada have also geological formations that are good for this type of hydrogen storage applications. And you have also other parts of the world, like North Africa, where there is some opportunity of development. For hydrogen storage completion, you need to have indeed pipe and connections that are leak tight to hydrogen, and this is a clear technical challenge. So we have worked to develop premium connection for this application that we have qualified under hydrogen, so under compression, tension, bending type of mechanical solicitation with hydrogen syngas and with 100% hydrogen as well. And we have started to run it on a couple of projects globally. So a few track record in Europe, some track record also in the US. But today we have in our portfolio a connection named VAM21, which is leak tight to hydrogen. And as you know, hydrogen is a we'll say the tiniest molecule that could be. So this is, in terms of safety, something that you need to think about when you are completing a hydrogen salt cavern for hydrogen storage. So connection and leak-tight connection is a topic. Another challenge is also material qualification for this type of application. And one of the key, I will say, issue related to material for this kind of application is hydrogen embrittlement. Hydrogen embrittlement under high pressure. This is something that steel are not immune to, and you need to have specific steel that have been designed to resist to this kind of issue. And in order to qualify our material in this condition, so we have run a number of testing from lab scale to full scale, among which mechanical testing are really important to test the steel and the pipe under conditions that it will face during the storage. Fatigue type of testing. When you are producing and injecting hydrogen, you have this fatigue type of solicitation, and fracture toughness also, the ability of the material to avoid crack propagation even in high hydrogen environment is also key. So those are the type of expertise that we have in-house in order to qualify materials and make sure that they are suitable and safe to avoid, I will say, any issue that we have been able to see in the industry. As you can see, a few of those pipe failure here in the US in 2024, I guess. And last slide would be an overview of where we actually have completed salt cavern in the world. So you have at least 4 salt caverns in Europe that Vallourec have completed, provided CTG, tubing, casing, and connections for this type of work. And same thing, we have also qualified a number of our materials for pipelines, so hydrogen transport in pipeline to make it safe and reliable transport up to our customer. So those was a few words I wanted to share with you about hydrogen pipeline and hydrogen storage.
Good afternoon, ladies and gentlemen, and thank you all for dedicating your time to this important forum. I would like to talk about the geophysical monitoring, and the first you may ask, isn't that too early to talk about it? And I want to show you this and tell you that no, it's not. So the state of Texas is already represent probably one of the states with the busiest subsurface, where we have a lot of things going on with the oil and gas, as you see on that map on the left, showing the existing wells. You can see a lot of things going with the groundwater, and as you know, that's one of the most precious resources that are, we're really trying to manage kind of better, and that's one of the biggest risks for the state as a whole. And the CO2 is hydrogen is coming additionally to populate all these middle floors in the subsurface, but essentially it's no longer a standalone houses on the hills. It's really a very, very tightly packed sort of high-rise with a lot of neighbors, and we all need to learn how to manage and live peacefully and safely, right, and achieve our energy transition and energy needs goals. And of course, Representative Derby and the legislature are kind of acutely aware of that, and as you know, the TexNet is a microseismic network run by the Bureau, is already monitoring induced seismicity around the state of Texas. But what I'm trying to tell you that it's, we're no longer going to wait until the induced seismicity comes up, because that's already a very late stage. We're looking for an active geophysical monitoring to know what is happening well before the problems become acute and require some drastic changes. So, and specifically in terms of hydrogen storage, as you saw, the salt caverns and the aquifer or depleted fields are the two major options, and both of them have significant risks. As you see on a picture on the left, that these salt caverns can grow with time. That's already been shown with the previous sonar surveys. They need to be monitored. The hydrogen can travel through some of these, connecting sort of formations. It can potentially contaminate the aquifer. It can create stress concentrations. All of that requires a careful monitoring and management. And again, we have to manage the interactions of all the going with hydrogen, with groundwater, and with other things. So all of that has to be in a context, and that is a very difficult task. On the aquifer side particularly, as you saw, that's a biggest storage potential in terms of volume. It's easiest, it's most cost effective, but it represents even more risks because the hydrogen is a lot more mobile than the CO2, right? And in case of hydrogen, we're really not in a business of storing the, like CO2 in the formation and letting it go any place it needs to go to be trapped. We really need to be able to recover it, and that represents an additional challenge, right? Because loss of hydrogen will be economic loss for our sort of, energy storages. So all of these things, and of course, induced seismicity, and all of these risks are similarly present. And again, this is something that is only can be, actively managed. So with geophysical monitoring, there are a lot of things that could be done in play. I'm not going to dwell too many of them. I just sort of list them in some, just to give you a flavor of what is happening. Obviously, there's a lot of attention to dam monitoring in the wells themselves. Particularly with the fiber optic technologies such as distributed acoustic and temperature and strain sensing. That's a very active area that is, represents a very kind of cost-effective way of monitoring things. Obviously, doing things with the surface techniques and particularly sparse monitoring is heavily sort of desired in the entire energy transition space. But how exactly to implement these sparse monitoring techniques, that is still a significant effort, because the techniques and technologies obviously exist in the oil and gas industry, but it's very difficult to transfer them into the energy transition space without significant kind of optimization. So the passive monitoring is already there with the TextNet, and there are a lot more sort of local things are happening there. And of course, monitoring the actual sort of hydrogen, appearing at the surface. So I just want to show you one flavor, what that would look like. So for example, this is the permanent source receiver systems applied for sensitive monitoring, understanding the scenarios of what is really sort of these molecules doing on the subsurface, and that is particularly relevant for our sort of upcoming field tests that we as a bureau is in the process of preparing for, and that's spearheaded by GeoH2 consortium that Mike mentioned, where we will be injecting a small amount of hydrogen in the aquifer to exactly de-risk all of these aspects. So in effect, it will become a mini sort of a shared laboratory where we will address all of this, risks with hydrogen, injection in the aquifer through the comprehensive geophysical monitoring program, and that is something that is happening. So in fact, yesterday I just visited our Divine site where we started a characterization survey. And with that experiment, we are, actively seeking, sponsors and partners who wish to participate in that and accelerate that learning. And we would be fully sort of sharing those results, and hopefully it will accelerate the energy transition path that we have. We have great support so far, and we're really eager to do what needs to be done, but contribute to this accelerated sort of schedule of adoption of hydrogen storage.
Well, thank you, Andrey, and Thanks, Capucine, and also Harold. And so I think what I'd like to do is, let me just state the questions that I posed at the beginning. Let's go through the panels with your thoughts, and then we'll open it up for questions that we might have from the audience. And so the questions, and feel free to choose the one you'd like to answer, but what are the biggest challenges for storage? What research is needed? And how could academic and industry collaboration facilitate solutions? So, Capucine, do you want to kick off?
Yeah, sure. So I think, and maybe it goes a little bit with what was said in the panel earlier today, is that there is still some like technical things that has to be like confirmed, and a lot of like research, like especially when we think of storing in porous media, like the reaction of hydrogen with like the water. And but what we are seeing today is that the biggest challenge for the project is economics, and for the project to make sense economically, I think that's, and I'm not expert in this part, but that's really like policy and regulation and actors coming together to like make it happen. I think that's what we see, at least on our side.
Yeah, I would agree with that. So Harold, how about you? What are the challenges? What sort of research is needed? What sort of collaboration is required?
So I will back up Capucine on the fact that indeed the legislation is needed, and tax incentive could be helping the development of the hydrogen value chain, especially supporting the offtake of hydrogen, because you have a lot of tax incentive that have been used mainly for hydrogen production, not a lot to support the use of hydrogen within the industry. And this can help indeed to grow the, I would say, the need of storage in geological formation mid-long term. So that would be a first step in terms of current challenges over the value chain. And coming back on the question about the research and the collaboration, yesterday the workforce topic was aligning the fact that university and industries need to work together to put the, I will say, the program in terms of research and training of new students that can be supportive for the execution of such projects. Therefore, corrosion expertise, electrochemistry, mechanical expertise, welding expertise are the type of research field or technical field that would need to be jointly developed in between the industries and the university to make sure that the new graduates can support the development of this industry.
Yeah, great. I like that you tied it back to education. Thank you. Andrey, what's your view?
I want to build on Harold, that's exactly what we're looking is for this new format to work across from, you know, UT and academic industries to with companies like Harold's and Capucine's, and sort of de-risk those things. But, you know, the best way to do it is to actually do things, right? And that's why, you know, this test that we're talking about, that's going to be a wonderful opportunity for our students, right? That's exactly to learn about these things and, you know, prepare the workforce for that energy transition through learning, but also de-risk those things that, you know, each company kind of struggling on their own, right? And de-risk it in an integrated fashion, because at the end, as you saw, there are lots and lots of things from A to Z that needs to be done. And it's very difficult for each company, like Harold is focusing on a specific band of the problems, right? But they obviously not able to address them. Whereas I think we, as UT, I think really can really be a glue, you know, taking all these ingredients and helping and working together to get that done.
Yeah, very good, Andrey. So with that, let's because we still have a few minutes, let's open it up to see if there are any questions or comments from the audience. There's one in the back. It's, I think, Pradeep. Go ahead.
Yeah, so Andrey, I'm curious about the natural hydrogen part that you showed in your diagram. Is there a site where you have like the hydrogen and then the cushion gas and the can you talk a little bit about what the natural hydrogen part was in that diagram that you had in the end on your slide?
So the question to me, Pradeep, is that the one? Sorry, you want to know about natural hydrogen?
I want to, yeah, so is there a site here with natural hydrogen present where you guys are going to do the experiments?
Oh, yeah. So the experimental site is for storage. So we just basically want to inject hydrogen and see if we can monitor it and see how the hydrogen plume behaves in porous media and aquifer. Separately, our group GeoH2 is also conducting research on the potential for natural hydrogen, and the Bureau is conducting a study on the possibility of natural hydrogen within Texas.
Maybe I can add a few words on the natural hydrogen. This is a trend that we have seen that is picking up. In Europe, you have the first exploration permits that have been delivered for, I will say, the regions where you have potential natural hydrogen. Here in the US, there is few startups starting to explore that. You have Coloma, for example, that is looking at this natural hydrogen. And in Mali, currently, you have one well producing natural hydrogen. If I well remember, it should be around 1 ton of hydrogen per month, and they are producing electricity out of it. And this natural hydrogen, if things and the research are, I will say, developing, and we, I will say, understand how we can produce it, this could be a game changer.
Very good. Question?
Two questions for Mr. Evin. Do you have the material selections that have been most applicable for hydrogen embrittlement in the salt cavern application? What materials have you used? And secondary to that, have you identified, has Vallourec identified any transition connections for line rock caverns to the internal liners?
So, line rock caverns, this is a topic that we have not addressed yet. But for salt cavern, indeed, we have this VAM21 connection that have been qualified for those applications. And in terms of chemistry that are resistant to hydrogen embrittlement, those are proprietary chemistries that we have in our portfolio that we have used for executing the projects that you have seen in Europe. So some with Gazuni, some with EWE, for example. So yes, we have in our portfolio current chemistry that show, I will say, good performance under high pressure hydrogen. So happy to discuss with you afterwards. Yeah.
Hello, my name is Hasib Abdullah. I have more of a layman question, if you guys don't mind. Isn't the promise of hydrogen trying to get to the democratizing energy? So gas stations will be able to electricize their own hydrogen. They're at the station, so you don't have to pump or truck that energy there. And just another question is, if hydrogen does leak, you don't have the same environmental issues, right? Like if oil or gas leaked in the aquifer, is that correct? Thank you.
Let's see, maybe I'll start. So, there are different models about how hydrogen can be generated, but at the scale that we're talking about, it's effectively, I'll call it an industrial scale. And most of the hydrogen today is generated through steam methane reforming and natural gas. These are large facilities, very large plants. China, there's coal gasification, again, very large facilities and plants. So, whilst you might have the opportunity for some distributed production of hydrogen, so where you might not need significant storage, I think that's going to be a smaller scale. Then the second question, yeah, leaks. So it was mentioned in one of the earlier sessions. So hydrogen plays a role as an indirect greenhouse gas. So then as a consequence, there is concern about not wanting to have rampant leakage of hydrogen because it has indirect consequences that could lead to at least short-term global warming.
And you have indeed issue related to the safety, so leak of hydrogen be highly flammable. So this is things that you want indeed to avoid. what is a good thing is that it dissolves also quite well in water. So you can build system with a water barrier, for example, as a second barrier to avoid any big leak of hydrogen.
Great.